is really inspiring and humbling yesterday to listen to Kanan and to see how much science has been achieved by people in this room. So I'm hoping to learn much more in the next few days from everyone. I have been asked by the SOC to talk about aspects of modeling the 21 centimeter signal. We have already heard quite a bit about this yesterday, but I guess they wanted me to get into a bit more detail in this talk. Uh, and so that is what I will do today. I will also show many science results that have come out of my own work in the last 4 years. And these results have been developed by, in collaboration with many people whom I have listed on this slide. I particularly want to highlight the hard work of my students, Shikhar Mittal, whom you heard yesterday, and Sindhu Satyavolu, and my postdoc, Janaki Raste, who has now moved to NCRA. So, to set some context, the overarching goal, as most of us will agree, is to look at this kind of a cartoon evolution of the universe and tell us that we want to compute the 21 centimeter signal from the epoch of reionization and the cosmic dawn. Those are the periods which I think Somnath defined for us already yesterday. But although that it's very easy to state that that is our overarching goal, we also have some further items on our wish list. We want to do this ideally throughout the cosmological parameter space. Ideally, one would want to predict the 21 centimeter signal for non-trivial variations in the model space. But on the other hand, we also want to prevent complex astrophysics from ruining our predictions. And all these beautiful dark matter and dark energy models that we heard about yesterday, we would like to understand how much these models retain their identity throughout the complicated astrophysics that happens throughout the epoch of reionization and cosmic dawn. So that's roughly the overarching goal, and many people have worked on this, and I will try to present it in my own the way I have been thinking about this. And that is to emphasize the basic physical relationship between the main signal, that is the target of SKA and all other cosmological 21 centimeter experiments, to the basic cosmological quantities. Somnath explained this yesterday. If you want the details, I recommend Somnath's beautiful YouTube lectures for the derivation of this. But the basic idea is that the differential brightness temperature has these three dependencies. There is a dependence on the spin temperature, the cosmological density, and the abundance of neutral hydrogen in the cosmological gas density, right? And so when we talk about modeling the 21 centimeter signal, that just means that we need to model these three things: the spin temperature, the cosmic density, and the cosmic H1 abundance. Of these, the spin temperature can be modeled by considering processes such as the Lyman alpha coupling and collisional coupling that we heard about yesterday. Although what I'm going to do in this talk is I'm going to talk mainly about the 21 centimeter signal that the SKA is going to target towards the in the epoch of reionization. And I would argue, at least for this presentation, that in this period one can reasonably assume that the spin temperature is much greater than CMB temperature. One would hope, we don't have empirical evidence for this yet, but it's a fair assumption to say that any heating processes by hard photons have already worked out by these redshifts. But then if that happens, the TS modeling becomes almost trivial, because that ratio becomes 0. And then you are left with delta and XH1. The delta is essentially the gas density distribution throughout the universe. But what's interesting is that on large scales, on scales above say a few tens of kiloparsecs, a lot of people have shown over the last 10 years that the gas density very faithfully follows the dark matter density. And this is very good news, because dark matter density calculation, even in the very nonlinear regime, is something we know very well to do. You can download high quality software and get this distribution on your laptop, as many of us in this room actually do routinely. So even I would argue that the delta evolution is also not that complicated anymore, at least on these large scales that SKA is going to target. That leaves us with XH1, where I think most of the interesting innovations are happening. Here now the task is now to compute the abundance of the um, neutral hydrogen. So if you want the 21 centimeter signal from an arbitrary cosmological model, you will compute TS or make this assumption. You will compute delta by evolving the dark matter structure, and then you will be faced with the calculation of XH1. It turns out that the calculation of XH1 is in some sense the hardest thing to do for the reionization epoch when it comes to SKA. And so this is something that I have been working a lot on in the last few years. So I'll focus my talk on modeling XH1. The discussion of modeling TS and delta is also interesting, but I will not talk much about that today. And so at a very high level, the calculation of XH1 has been attempted in two different ways. People have either tried what are called semi-numerical approaches, and we heard a bit yesterday about these, and I'm sure we will hear more in this meeting. And this has been contrasted by some people who have been trying to do almost ab initio simulation. Okay, so let me make sure that we understand what these two approaches are, because understanding these two approaches, I believe, will allow us to make rapid progress by teaching each of these techniques from others to reach more accurate and reliable models of 21 centimeter. So when I say semi-numerical, what this means is that semi-numerical models often involve postulating recipes that lead to neutral hydrogen abundance, and these recipes are not necessarily obtained from fundamental physics calculations. These recipes are often calibrated by some data. It might not be 21 centimeter data, but by some data or by some ab initio simulation. Okay. And ab initio simulations avoid doing that. They are not always successful in avoiding this recipe business, but they want to at least they aim at avoiding that. And what they instead want to do is solve elementary physics equations with known initial conditions for getting XH1. So these are the two approaches. This simple choice, because it's a complex system, this simple choice between these two approaches leads to a few properties which are important to understand. For example, in the semi-numerical models, there are a very large number of free parameters because each recipe comes with its own set of free parameters, and these are often set by hand with some intuition coming from some observation, or marginalized like we saw in Atri's presentation yesterday. Ab initio simulations, because they start from elementary equations, they have fewer effective processes, therefore the number of parameters can be small. There are advantages to large number of parameters, but there is also advantages to having small number of parameters. Oops. The most important distinction, as many of you know, between these two approaches is the semi-numerical calculations are really fast, but the ab initio calculations are very slow. In fact, until about 5 or 6 years ago, they were almost useless because of their computational cost and inefficiencies. So this is an important distinction. But then there are a couple more distinctions. One is, this is an important point which is not often realized, which is that the semi-numerical approaches are by necessity static. They are unable to evolve quantities very easily. Although attempts have been made, propagating physics from one redshift to another is very hard in semi-numerical approaches. You have to do some kind of a calibration to do that. Whereas ab initio simulation, because they are fundamentally dynamic, because you are essentially solving a bunch of differential equations, they are dynamic. And so if there are non-instantaneous processes, and reionization is one such process, it's non-instantaneous. Edges showed that in its first year data. Ab initio simulations are often better to understand those. So there are some examples: 21 centimeter fast, Script, and Reion Yuga, which have been mentioned here, are examples of semi-numerical approaches. And ab initio simulations are, for example, the Tayson's suite, the Sphinx, and the simulations that we have been running, for which we haven't found a nice name. Before I proceed, I want to make sure that the contrast between these two approaches of calculating the neutral hydrogen abundance is understood at the right in the right spirit. I don't mean to say that one approach is necessarily superior than another. Okay. For example, the semi-numerical approach needs ab initio simulations to calibrate its recipes. But on the other hand, ab initio simulations cannot take a holier than thou attitude. They also make several assumptions and calibrations. Okay. We don't have a fundamental physics simulations that starts from standard model and gets us reionization yet. Okay. So what I'm going to do now is I'm going to explain how the 21 centimeter signal is modeled in an example ab initio simulation. This is because this is something I have been working on recently, and then I will give you a flavor of what the results look like. Okay, so as I said, ab initio simulations want to start with elementary equations rather than recipes. And for XH1, we know what sets it is essentially radiation physics during the epoch of reionization. So we have to compute radiation physics, and radiation physics is computed in astronomy by means of the radiative transfer equation, where you postulate a quantity called I nu to quantify radiation in a problem, and then the I nu the evolution of I nu can be described by a differential equation like that, where there are 3 terms on the left hand side, 2 terms on the right hand side. These terms, the first term here describes the temporal evolution of the intensity of light. The second term describes the spatial evolution. Third term describes the effect of cosmic expansion. And on the right hand side of the equation are 2 terms which take care of the source and the sinks of photons. And so the goal of these ab initio simulations is to now get us initial conditions and solve this equation. Okay, and the hope is not much will be required. The problem is doing this is really hard, and there are 2 main challenges. One is it turns out that the simulations that we need for 21 centimeter in particular need to have very large dynamic range. By that I mean that the simulation has to be very large in volume, but it at the same time should also have very small scale resolution. And the reason this is the case is because the reionization physics, the scale at which radiation operates in reionization, as well as the scales that we are interested in SK, are these large scales. But the right hand side terms in the radiative transfer equation, the kappa and the J term, the source and the sink term, actually are all set at very small scales. Okay? And so the dynamic range is a challenge, and this has prevented progress for many years. But then there is also a second challenge which relates to this property that I highlighted of dynamicness of these simulations. Because this is a temporal differential equation, it turns out that you need if your resolution is very high, the typical spatial scale in the numerical computation is very small, something that I have denoted here by delta x, and the time scale at which, the time step at which you will have to sum the differential equation for a convergent numerical solution is delta x by c, and c is a large number as we know, and that slows down the calculation. So we are unfortunately in this worst case scenario where the problem is big and the problem is slow. Okay, and so most of the work here has been to discover techniques that allow us to solve this problem, and it is these 2 problems that actually motivate all the semi-numerical approaches. These 2 challenges are the reason ab initio simulations haven't been very popular until now. People have come up with various algorithms. These are the names of various codes in which these algorithms have been implemented to tackle these 2 challenges in ab initio calculation. But these algorithms can be classified in 2 broad categories. Either they are ray tracing algorithms, in which you trace rays in the simulation box from each radiation source to each radiation sink, and compute the solution of the radiative transfer equation along each ray. And then there are moment based solution in which you don't do that, you actually solve averaged versions of the radiative transfer equations. The properties of these 2 algorithms are very different. As you can imagine, in ray tracing, the accuracy of your solution will depend on how many rays you trace. And therefore, the computational cost goes as the number of cells, the number of points in the simulation volume multiplied by the number of sources. And in reionization, the number of sources are billions and the number of cells are billions, if not more. Interestingly, the moment-based method, and this was actually shown a long time ago, but was realized in cosmology only around 2010, the dependence on the sources goes away because of the averaging, which I will try to briefly explain in a second. And so your property, your efficiency of the simulation now just scales as the number of cells, which means it just scales with the volume. And this breakthrough has allowed us recently to do really high dynamic range simulations. This has proven to be a really good response to the challenge of dynamic range. Interestingly, the challenge of the time step, the speed, the time required for the calculation could also be solved indirectly thanks to the moment-based method. So what I have been doing in the last 4 years is doing a variety of moment-based simulations of reionization. I will give you a flavor of what we are doing in that. But before I proceed, here is the rough idea. I wrote down the radiative transfer equation a few slides ago. In moment-based radiative transfer, you actually throw away that equation and you come up with 3 new equations. Okay, these 3 new equations are angular moments of that partial differential equation. So, for example, this is the 0th angular momentum, where you get a differential equation instead of in I nu, you get an equation in n nu, which is a scalar quantity denoting the number density of photons at each point in the box. And the second equation is obtained by taking another moment, angular moment of this first equation, and this is a dynamic equation in f nu, which is a vector quantity which denotes the flux of photons. Now you can keep going like that and get a infinite hierarchy of equations, but what somebody showed in 2007 and 2008 is that if you can take a certain choice of this little tensor that appears in the second equation, which is called the pressure tensor, then you can close this system of equations. So this third equation is actually an assumption, a bit like the recipe of semi-numerical approaches. Okay. And then if you plug this in, you have a closed system of equations. And it turns out that this method works quite well in doing cosmological radiative transfer. What's very interesting is that you will notice that these 2 equations are very similar to the equations of fluid dynamics. And so radiation in this approach is actually like fluid, which is why the dependence on the sources goes away. This has some advantages and some disadvantages. So these simulations, for example, can be quite inaccurate at small scales. Okay. So what I have been doing is performing these moment-based radiative transfer on top of a cosmological hydrodynamical simulation using a code called ATON. This is a code that I have not written, but my group has extensively modified. It was originally written by a French group of Aubert and Tessier in 2008 and 10. And the moment-based method that is used, the one that I described, has a name. It is called M1 closure for historical reasons. Note that our simulations, these are the kind of simulations that we do. These simulations, as I said, can be done by anyone. We are confident, fairly confident that these simulations are accurate, at least on the scales that SKA is interested in. And notice that the dynamic range of these simulations, as promised, is quite large, 160 megaparsecs over H to about 80 kiloparsecs over H. Okay, so this nicely spans the scales that SKA will be sensitive to. And most of the simulations that we did previously, and I think most of the results in today's talk will be for a simplified IGM, although now we have done simulations that has a realistic IGM. And so just quickly, this is how reionization looks like. This is a sort of a video animation counterpart to the animation that we also saw yesterday. What is shown here is the temperature of the intergalactic medium and the neutral hydrogen fraction of the intergalactic medium evolving in redshift. What I haven't said, of course, is with radiative transfer, you also do the thermochemical calculation to compute. I'm not going to waste time in letting this finish. I'm sure every one of you can visualize what happens at the end. But I'll quickly go on to say that what's really interesting is that the particular choice of pressure tensor was also interesting to meet the second challenge of speed. The tensor that we chose is local. It only depends on quantities at one point. The tensor at a point only depends on the physical quantities at that point. This means that the problem can be split in multiple chunks, and each chunk can be sent to a different processor. And this is very handy if you have GPUs. And in fact, with GPUs, you get close to 2 orders of magnitude enhancement. So you haven't gotten rid of this delta x by c limit, but you have managed to execute each step 2 orders of magnitude faster. So this is how this approach allows us to solve both challenges of the dynamic range as well as the speed. So this is roughly the method of these simulations. And now what do we do with this, right? And so the idea now is to use this kind of an approach to get XH1, plug that into our 21 centimeter formula, and get our predictions for 21 centimeter cosmological experiments. What I want to emphasize, and this is something I have been focusing my attention on in my research group in Mumbai, is that we can now use the ability of this model, that is kind of its strength, which is to predict many observables simultaneously and self-consistently. We don't need different recipes for different things. It not only predicts 21 centimeter, it predicts everything related to the IGM that an observer could observe. And I think that's the strength which one should exploit when doing this, instead of doing other things where this approach might not be very good at. So this is what I have been focusing almost obsessively over, as I will show it by means of some results soon. And the hope that I have is to sort of take steps towards a simple unified model of IGM during the EOR. By unified here, I mean an IGM that is consistent with as many observations, so that you can bring information from a variety of data sets when you constrain models using 21 centimeters. And so I will now show how that comes about, and for that I have to quickly introduce the concept of Lyman alpha forest. I don't think we have discussed this yesterday. Some of you may know this very well already. But the Lyman alpha forest is another way of measuring the XH1, similar to 21 centimeter. Okay, it's a complementary way. Somehow this works where 21 centimeter doesn't work, and 21 centimeter works where Lyman alpha forest doesn't work. But the basic idea is very simple. You have a bright source which you see through a very good quality telescope fitted with a good quality spectrograph, and then what you see is a spectrum of this bright source, right? Typically the source chosen is quasar, but it doesn't have to be. And then what you see is that as you go to farther and farther cosmological distances, these quasar redshifts show this dense network of absorption lines. Okay, so this is a quasar close to us, this is a quasar farther from us, and you can see that the farther quasar has this dense network, and this has been interpreted as the signature of Lyman alpha absorption by the small neutral hydrogen atoms along the line of sight. Okay, the Lyman alpha transition. And if you have a very good quality spectrograph, you can resolve these Lyman alpha lines. Prakash does that for a living. And then once you do that, you can measure various physical properties of the matter around this sight line. And this has been done. And ideally, what you could now do is just keep on doing this and map the epoch of reionization in the period where we want to detect the 21 centimeter. The method has been supremely successful. In fact, it is one of the best methods we have of doing cosmology today. But unfortunately, this doesn't work at high redshift of about 6 is where it stops failing. Even if you have a quasar, above redshift 6, it doesn't work. And the reason it doesn't work is because at that point, this Lyman alpha absorption is so severe that the whole chunk of the quasar spectrum is wiped out. As you can see in a bunch of quasar spectra, these look very different from the spectrum I showed previously. And here you see that most of the spectrum is just gone. And this is why this method stops working. But what has happened recently is that we have found a way to actually extract information about the epoch of reionization from at higher redshifts from low redshift Lyman alpha forest. And we have been using that in our predictions of the 21 centimeter. And how has this come about? This has come about from a very different angle. What people found was that although these Lyman alpha forest lines get saturated and wiped out at redshifts of about 6, this doesn't happen for all lines. They found that some lines remain transparent, So these two quasar sightlines are at the same redshift, and you can see that the curve shown in black is quite transparent, but that shown in red is almost completely wiped out. You can quantify the amount of absorption by defining a mean transmission, mean flux over a length scale. People typically choose 50 co-moving megaparsec. You can also quantify the negative logarithm of it as some kind of a mean opacity. And then you find that indeed what happens is that at low redshift, at redshift of about 4, this mean opacity is roughly similar for all sightlines. But as you go to higher and higher redshift, there is a large fluctuation. There is almost a factor of 500 fluctuation in the mean flux from sightline to sightline. And you can see that this experimental data stops at around redshift of 6. What we found using these M1 simulation was that this scatter has information about what reionization is doing at these higher redshifts. Okay. So the way this came about was that what was noted was the following. If you plot the same data point shown on the previous slide now as a distribution function of the tau effective at 4 different redshifts, what you find is that at higher redshift the spread is very large, as I said before, and the spread is totally in a total disagreement with models in which reionization has completed much before than redshift 6. And this is the point of attack from which we can start getting information about when reionization happened from this distribution. And indeed, we found that if you delay reionization in down to redshift of 5.3 in these M1 simulations, you beautifully recover the distribution functions that observers measure. What is shown here is again this effective opacity, the mean tau as a function of z, and the blue shows the simulation and the red shows the data, and here are these cumulative distribution function, again blue shows the simulation and red shows the data. And this is the only picture that has explained these behavior of the Lyman alpha forest. And so in fact, if we plot light cones, here I show the XH1 temperature and photoionization rate. What we have been learning in the last 4 years is that there is almost no freedom left in the reionization out to redshift of 7.5, which is remarkable because your Lyman alpha forest measurements stop at 6 at most, right? But you have very tight constraints now just from the spatial scatter in the Lyman alpha forest out to redshift 7.5 or so. Now, I want to come to 21 centimeter from this. This is our XH1 which we were after, and now the plan is to plug this in and get our 21 centimeter signal. But I just wanted to emphasize one thing which I think has not been maybe sufficiently discussed in the 21 centimeter community, which is we are now starting to believe that there is some truth to this picture. Although we had this pressure tensor which we kind of cooked up, there is perhaps some sense in this picture of reionization, because this seems to be a concordance picture. It has become very hard to break down this plot. And no matter which observational measurement you throw, this seems to agree with it. In fact, it's for the first time that many different observations have been explained by one reionization model. So I just want to spend a couple minutes on that before going to 21 centimeter. So for example, in this plot, what I'm showing first is the CMB optical depth, the Thomson scattering optical depth to the last scattering surface. And the red band is the Planck measurement, and the blue is this model. Okay. What is shown on the left panel here is the volume fraction occupied by the ionized region, the QH2, as a function of redshift. The blue curve is this model, and you can see the predictions from a model by Tirthankar Choudhury and the inferences from various data sets. For example, these 3 points are from quasar damping wings at redshift of around 7, and these 3 are from dark pixels in the Lyman alpha forest. So you can see there is a beautiful agreement between this model and the other models. In fact, it started to get even stronger because then to test this model, some observers did the following. They said, okay, you have got my spatial scatter in Lyman alpha forest, right? I am now going to count the number of galaxies around these sightlines. Okay. So you take the sightline and you calculate how many galaxies exist around that sightline, and it turned out that that also is perfectly consistent with this model. These black are that sightline is the number density, surface number density of Lyman alpha emitting galaxies around the sightline, and the blue is the is the simulation that I showed. It kept going. This is why we kept getting more and more confident that perhaps this is really something interesting. It became possible to measure the Lyman beta forest for 19 quasars for the first time at around redshift 6. And these are the measurements now shown as the Lyman beta tau as a function of the Lyman alpha tau in 3 redshift bins. And again, what you are seeing in red are the data points, and in blue, the simulation. Okay. In fact, the hardest one, because of its astrophysical complexity, was the luminosity function of Lyman alpha emitting galaxies. These are just normal galaxies. All galaxies emit Lyman alpha. These are galaxies selected by the observer based on their Lyman alpha emission, and because that is how the selection is done, the number density of these galaxies depends on the IgM, because Lyman alpha is attenuated by the IgM. And so, elementary statistic to study these galaxies is the luminosity function, and this is shown here in 4 redshifts. And what you can see now is the simulation model that I showed agrees reasonably well with these data. Okay. In fact, once the simulation was done, we started a large program on the VLT telescope, which has a very nice spectrograph called X-Shooter, to get, for the first time, a uniform, very high quality sample of 30 sightlines at redshift greater than 5.7. And these new sightlines also are beautifully in agreement with this old model. In fact, the new sightline really identifies very strongly the redshift of 5.3 as the end of reionization. Okay. Just to conclude my sort of the marketing spiel of this reionization model, finally, we have also been working on understanding whether the explanation of Lyman alpha forest structure using late reionization holds if we relax our M1, and it continues to work. For example, here are some ray tracing calculations. The ones that I told you are very slow. Here are some excursion set calculations similar to script and 21 centimeter fast. And here is a higher resolution M1, the Thiessen simulation, which has much more physics than our simulations. And I don't have time to go into the detail, but every one of them seem to favor this redshift 5.3 and 2 reionization. So there is, the reason I'm showing all these things is that there are 2 reasons I'm showing all these things. One is to show how ab initio simulation can predict a very wide variety of observables without extra investment of effort. You have to do just one calculation and it predicts 10 different things. And the other is, it seems that this particular model using ab initio simulation seem to tell us something about the epoch of reionization that we intend to model for the SKA. And that's what we did with the help of Janaki Raste. This is now the 21 centimeter signal from the simulation that I have been showing you, assuming efficient X-ray heating. So the spin temperature is much greater than CMB temperature. And you can see, for comparison, a traditional model of reionization which has been discussed in SKA and HERA papers. This is the Hart and Maddow model. You can see that the structure at redshifts 5 to 8 is significantly different between what was traditionally considered a good reionization history and what these new models are telling us. In fact, if you look at the power spectrum now, we understood what power spectrum is from Somnath's lecture yesterday. This is showing the power spectrum at redshift about 5.6, and this is at 5.4. And what you see is that just because you have this extra structure, the power is enhanced by orders of magnitude at these redshifts compared to the previous early reionization models, and you start coming, you start becoming sort of detectable with SKA in principle. In fact, a better representation that I like is this. Here are all the upper limits published on the 21 centimeter power spectrum below redshift 10, including the latest HERA limit here. And you can see that what this model has done is, the model I have discussed is shown in the solid curves, and the traditional models are in the dashed curves. What it has done is it has pushed everything towards lower redshift. And interestingly, the signal, we think that the signal should be very interesting in the bispectrum, because these high opacity, high Lyman alpha opacity regions are the most non-Gaussian places, the extreme voids. And so we have been looking at bispectrum a bit. Indeed, the bispectrum signal is very strong, It's essentially a shifted bispectrum. What we would have expected at redshift 7 now occurs at redshift 5. This should be an interesting thing to further understand. So I'm keen on talking to bispectrum experts in the audience about this if possible. I want to conclude by giving again a strong sense of the power of this method in predicting many observables simultaneously. I've already shown a lot of observables. I want to show a few more observables which are where the data is only coming now or will come in the future. So, for example, there are measurements of what are called quasar proximity zones, which tell us about environments around quasars in the epoch of reionization. And this is the main statistic measured in these experiments called the proximity zone size RP. And this is the lifetime of a quasar. And what we are finding, if you compare the blue with the green, is that the patchiness of reionization at these low redshift seems to have an effect on the proximity zone size. This has had interesting sort of repercussions for our understanding on how black holes grow, for instance. Here is another such prediction. This is something I'm keen on discussing in one of the discussion sessions. One can measure the cross correlation of galaxies with the 21 centimeter. This is something we have been looking at because as I was discussing with Somnath over lunch yesterday, I kind of feel that this would be the one smoking gun signature of a cosmological 21 centimeter detection. And so we have found that it should be possible to cross correlate SKA 21 centimeter signal measurements with Subaru PFS, which just got switched on 2 weeks ago, I think, on Subaru. So PFS is a spectrograph on Subaru, which has a very large field of view. So you observe a field and you cross correlate with SKA. Because Subaru is south enough, it should be possible for doing that. So this is an example of this cross correlation. What is shown here is the cross correlation in the top panel at various redshifts between Lyman alpha emitters and the 21 centimeter signal and the signal to noise. So you can see that SKA PFS and SKA PFS Hera both should be able to detect this cross correlation to a very high sigma. Okay. In fact, the cross correlation is also sensitive to reionization history. Here we have considered 2D reionization models and shown that they respond because of the sign change in the correlation, they respond very strongly to changes in reionization history. This is the same plot as before, but now comparing what happens if you change reionization history, and because there is a sign change, it should be possible to discriminate these very well. There's also some CMB science you can do. For example, a problem in CMB science has been to measure the B mode signal in the CMB, the B mode polarization signal. And here reionization is a nuisance because they want to detect the primordial B modes to constrain inflation. This is a crowded plot, but what this is showing is the power spectrum of the B modes as a function of L, and this is now the prediction. And many of the previous curves are semi-numerical predictions from various models. This is for the first time that we are now seeing perhaps more reliable predictions for B mode for reionization, which might help clean up these CMB maps in future. Okay. There is also a cross correlation from CMB SZ maps. What is shown is the Compton Y parameter here in broadband and narrowband experiments, where you find galaxies and in a broadband or narrowband band, and then cross correlate with a SZ map. This should also be a very interesting probe of reionization, although this one requires pretty future generation, future experiment. This is my last slide before the summary. This is something I was keen on getting opinion from the experts in the audience as well. These neutral islands are very interesting now because the number of radio loud quasars above redshift 5.5 is now greater than 50. So for the first time, we have a lot of radio loud sources. And so we have been trying to understand how the radio spectra of these sources might look like. And it turns out that they will show a lot of 21 centimeter absorption. So this will be a 21 centimeter forest now in the spectra of these objects. Of course, this will be very sensitive to what we assume for the spin temperature, and therefore the heating efficiency Fx. And so the simulation cannot make a unique prediction. The prediction depends on this fx parameter. But we found that null detection with 10 sources at SKA will constrain the reionization very well. And so this is something that we are really keen on understanding in future. So I'll conclude there. I hope what I have shown is that one can model the 21 centimeter signal from the EOR either semi-numerically or using the ab initio simulation. And what I wanted to do in this talk was to emphasize the ab initio side a bit more, because that's what I've been working on recently. But more importantly, these latter simulations are now for the first time also big enough. They are actually for the first time a serious tool to understand the 21 centimeter signal from the EOR. These simulations are slower, but they have now improved. And I think what I want you to maybe take away is these simulations are really good to understand multiple observations self-consistently. In fact, if there is a new observable tomorrow, you can go back to these old simulations and understand it. You don't have to develop new recipes for new observations. I think that's the sort of killer feature of this approach. And what I have also tried to convey, I hope that applying this technique severely constrains the 21 centimeter prediction space. We now know the reionization history out to 7.5. And that is a very useful prediction for SKA. And because it tells us that SKA signal will probably peak at higher frequencies than previously thought. I'll stop there. Thank you.
Questions for Girish?
So do you develop this pressure gradient force in your simulation?
You mean the pressure coupling between the gas and the radiation?
No, even the radiation itself, right? I mean, if you,
right.
Some places you like the neutral, the boundary of the neutral and the ionized region.
Yeah.
The pressure, there will be a zero pressure in the neutral region, and there will be a pressure at the ionized region. So will there be a pressure gradient term in your radiative will there effectively be a?
Yeah. So the pressure is basically, we have only studied it at very small scales, and the reason has been that the coupling between radiation and hydrodynamics is not yet implemented in these simulations.
No, I'm just talking about the I mean, you have a radiation field, right? Just like a fluid field.
See, yeah.
And I presume these equations are just like the fluid.
That's correct.
Fluid equation, right?
Yeah, yeah.
So in the fluid equation, if you have a difference of pressure, there is a pressure gradient.
Yeah.
So this will be there in your equation.
This will be there. Yeah, yeah,
yeah. So there will be a kind of effective force on the fluid.
That's
radiation fluid
right. Yeah.
Between at the boundary of the ionized regions.
That's correct. Yeah, yeah.
Which will try to push it.
This is why,
outwards,
for example,
right? We make it bigger than it should.
So what we have found is that at large scales, the pressure effect is not going to lead to significant inaccuracies. The result of the fluid dynamical calculation seems to be identical to a ray tracing calculation. It only affects in the regime where you have very few sources. If you have two sources, the pressure gradient is very strong. Or for example, if you have an opaque slab, the pressure gradient creates artificial artifacts that are wrong. What we haven't yet noticed any large scale inaccuracies because of these pressure gradient. And I think the reason behind that mostly is that the inaccuracies due to multiple sources and absorbers is probably having a cancellation effect on large scales. There is another pressure related inaccuracy that comes in these simulations, but that comes in the other regime after reionization is finished, where you see a sloshing of the radiation field on the periodic box, and that is because of this. That again doesn't happen until there is full overlap.
And do you also have, I mean, do you also develop diffusion and viscosity?
Well, diffusion and viscosity is present there. Yeah, we haven't analyzed it.
You have radiation diffusion and radiation.
But we do have radiation diffusion and radiation viscosity. That's correct. Yeah.
it's slightly related. So when we are trying to close those radiative transfer equations, the pressure tensor had an off diagonal term, right? So was that solely determined by some effective viscosity, or like?
Yeah. So the pressure tensor there was actually derived for a situation that has almost nothing to do with reionization. So it's slightly miraculous that it works, and we don't yet understand that it works. This is what I said was the recipe bit in the radiative transfer algorithm. In fact, we are going through and we are trying to understand a bit more whether it is related to viscosity and so on by two approaches. One is we are trying to understand the differences when we completely change the pressure gradient, the pressure tensor to very different forms. This particular pressure tensor is the pressure tensor for a point source emitter Lorentz boosted to another reference frame. So those are the two terms, but that has nothing to do with reionization in principle. This was something just postulated in the 1960s by someone for stellar physics. So we are trying to do that, and the other thing we are trying to do is compare it with post-reionization perturbation theory calculation, which we tend to trust. There we are finding that the pressure tensor that we have chosen at post-reionization, it does lead to about 20% inaccuracies on scales below the mean free path of these photons. So this is something in progress. I don't have much understanding of this yet. What I can talk more if you want later.
Thanks.
Hey, so I wanted to just ask, I understand that your radiative transfer code is pretty fast when you use GPU. But are you thinking of using any machine learning technique on that to make it more faster?
Yeah, I mean, I think, yeah, that's the question everyone asks these days. We haven't done any work on that direction yet. I have been told that it should be an interesting application. I think the closest people have come to doing that is actually the French group. They have emulated machine learning algorithms on many simulations and then used it. I think maybe there are collaborators of them here. Benoit Semelan and others have done a lot of work. That is promising, but I haven't thought too much about that myself.
Okay, so as far as I understood, that reionization can end as late as, let's say, 5.3 or so. So, but is there any thought how what's the allowance you can give? I mean, is it possible to go beyond 5.3 or so, or is it possible to go larger than 5.3 or so?
Yeah, so I think you are asking what the uncertainty
Yes.
is on this inference of redshift of reionization. So as I said, one of the weakness of these methods is that you can't span the parameter space efficiently. So reliable inference has not been yet possible. But we have spent millions of GPU hours in the last 4 years, and we have now done 12 such simulations.
Okay.
And they vary a lot of parameters that are allowed to vary. And we find that every time we get the same reionization history. The only thing that we don't understand in the epoch of reionization now is the temperature. This is where Prakash has been contributing. But we found that even wildly different temperature histories seem to give the same reionization history. And I think the reason is very simple. It's basically the Lyman alpha forest scattering is just such a tight constraint that you can't, it doesn't leave much freedom.
Thanks.
I don't come from physics background, so more like a machine learning background. So my, I mean, for the same data, do you have any results that comes from data-driven approaches so that you can compare your prediction quality? So, say some of the things I was trying to follow that. Say using your model, you have computed the number of sources, right? Now, using the same data, do you have any results that come from data-driven approaches to compare the prediction quality of your model?
Right. So maybe if I have understood the question, I can say a couple things. One is there have been parametric data-driven approaches. These are essentially semi-numerical approaches in guise. And that is something I showed towards the end of my talk. Here, what you do is you come up with parametric model. For example,
not essentially parametric. Say for example, some of the researchers I have seen that they are presenting results using neural networks, right? So, is there any way to compare results what you get from your model and those completely data-driven approaches where almost no physics is involved?
Yeah, I mean, I think I'll have to think a bit about understanding the question. But there are a few quantities which are, if I understand you correctly, there are a few quantities which are in some sense direct data products. They are as close
right,
as data
right,
product without involving a physics step.
Right.
And that's kind of what this tau is, for instance. So you can think of the distribution of the mean opacity as data-driven inference. Unfortunately, none of the observables are the parameters that the physicist is interested in.
That is true. That is true. I mean, the kind of analysis you want to do to try to understand the situation. So these approaches will not give us that scope. But just to compare prediction accuracy, that is there any result available?
I don't believe anyone has done this. Maybe I should understand a bit more.
Thank you.
Maybe after. Okay, thanks, Girish.